Yeah, in previous lecture we studied what causes magnetic spin alignment, like a ferromagnetism and antiferromagnetism. The main cause of the magnetic spin ordering is the exchange energy, because from the quantum mechanical point of view, and the exchange energy between the two neighboring spins, the exchange energy favors for spin alignment, spin up or spin down, and it is called from the Heisenberg model. In this time, we will think about that real magnetic order, the magnetic property of the magnetic order. For example, there are ferromagnetism. Ferromagnetism is that all the spins aligns in a certain direction, and like this, it is a ferromagnetism. Antiferromagnetism is that magnetic spin alignment is the antiparallel with each other. It is antiferromagnetism. Ferromagnetism is that is kind of antiferromagnetism, but the phenomena is like a ferromagnetism. In this case, the spin up spin is like this, and down spin is small, and there is a sublattice for the spin up sublattice and the spin down sublattice. The magnetization, total magnetization of the spin up sublattice is greater than the spin down sublattice. We call it as a ferromagnetism. As you know, the crystal is a three-dimensional materials, and therefore, in many cases, there is a possible mixed phase between ferromagnetism and antiferromagnetism. For example, in the three-dimensional crystal structure, and there is a layered structure. Assume that in the within plane, the spin aligns in a ferromagnetic order like this, but in the outer plane, in plane direction is ferromagnetism, but the outer plane direction is the antiferromagnetism like this. Then it is antiferromagnetic order, but the in-plane direction is the ferromagnetic order. It is ferromagnetic order. Therefore, spin structure can be many spin. There are many possibilities. For example, in this in-plane direction is the antiferromagnetic order, and the spin direction along the outer plane may have the ferromagnetic order. It is within plane, and the other plane, and the spin structure is like a ferromagnetic order. And also in the antiparallel for each spin can be possible, and in this case, in red arrow indicates that in plane direction also anti-parallel, and outer plane direction also anti-parallel, and there are many possibilities spin structure, and basically in many cases there coexist the ferromagnetism and antiferromagnetism, and also there are some spiral spin structure in the frustrated spin system, and there are many magnetic orders in magnetic material in real system. But here we just only focus on the basic magnetic order. Here, let's discuss for the ferromagnetism at first. Various spin structure or spin order like spiral spin and frustrated spin system is another topic that should be investigated as a separate research topic, which is very important in the contemporary condensed matter physics, such as the skyrmion. Skyrmion is like a spin flux, and it gives rise very profound physical properties like a Berry flux and Berry curvature, topological order, and so many interesting topics can be possible in the various spin structure. But ferromagnetism and antiferromagnetism is a basic magnetic order, and also here we only discuss for the ferromagnetism, ferrimagnetism, antiferromagnetism. At first, the ferromagnetism is that spontaneous magnetization. Spontaneous is important. It means that in the absence of an applied magnetic field, a conventional magnet that is attached in our refrigerator is that a real ferromagnet. And the real ferromagnet, we do not apply the magnetic field in the outside. And the material itself shows the spontaneous magnetization that causes the very hard magnetic field that generates the strong magnetic field in the materials. We call it as a ferromagnetic materials. The reason why the ferromagnetism shows exhibiting the magnetic order is that all the magnetic moments are lining up in a certain direction. All the magnetic moments or spins lie along a direction. As I said, the original ferromagnetism is the exchange energy, and therefore the Hamiltonian can be written down as a Heisenberg model. Then in this case, the Hamiltonian is that the Heisenberg model for Ij spin nearest neighbor interaction, and the Jij is the exchange integral, Si that Sj is the spin-spin interaction, and plus by applying magnetic field there is a G1 energy, G mu b summation for J Sj. Here by applying magnetic field, here Jij is positive. In this case, the first term is the Heisenberg Hamiltonian, Heisenberg exchange energy. Second term is the G1 energy. By applying magnetic field applying magnetic field B, then in a certain spin Sj aligns along the field direction, and the nearest neighbor interaction for the Si that Sj it makes the exchange energy that causes the magnetic order or the spin alignment. Especially for J value is important, and J value is like exchange energy. And here the positive exchange energy means that spin alignment along the same direction is energetically favorable, because S dot Sj should be positive because it is minus sign for the positive exchange energy. And therefore, in here, in the Heisenberg Hamiltonian, the exchange energy is positive. In this case, it generates that same spin alignment. For example, Si, Sj, spin direction, the Si dot Sj becomes positive and same in the same direction, and therefore it is Heisenberg model is very fundamental Hamiltonian. We already discussed in detail in previous lecture, and before the before the Heisenberg model, and Heisenberg, Heisenberg is one of the developer of quantum mechanics, and also before the quantum mechanics, and from the classical point of view, like a semi-classical treatment was applied in the magnetic materials. And one example is a Weiss model. Actually, Weiss model is a phenomenological point of view, but actually it is not correct in quantum mechanics, quantum mechanical point of view, but we can understand phenomenologically, whether intuitively, and therefore Weiss model is very fruitful to understand the basic property of the ferromagnetism. And anyway, then when we consider for the Weiss model, we call it is called also as a molecular field theory, and the molecular field theory is not correct in terms of quantum mechanical point of view. But in the Weiss model, when we consider the molecular field can be exchanged by the exchange energy, can be replaced by exchange energy, and the real thing is the exchange energy. But Weiss suppose that there are molecular field. Thus, one spin generates magnetic field, and the generated magnetic field can be affected with neighboring spin, and also it causes the field alignment of the ferromagnetic interaction. But it is not correct anyway. It is not causes. In that case, the magnetic field that generated by the single spin is too weak to describe the ferromagnetism, and therefore the Heisenberg considered the exchange energy, and the exchange energy is enough to describe the magnetic spin alignment. And anyway, and effective molecular field, we assume that at the right site. And in the Weiss model, say that one spin generates the magnetic field. Anyway, magnetic field, and it affected with the other spin, and the other spin also affected by the spin interaction. The spin interaction may causes the energy magnetic field, but it is not correct anyway. But in here, and when we treat as the magnetic molecular field can be considered as an effective field, the spin interaction can be considered as an effective field, then the mathematically it is convenient, even though the physical picture is not correct, and for mathematical convenience, and we assume that there is an effective molecular field. And here, let's define that BMF is the molecular field. It generates from the spin Sj generates spin Si, spin Sj generates magnetic field. That is the molecular field. Here, let's define that 2 over G mu B over for each spin Sj, J, Ij, and Sj. Spin Sj generating the molecular field, but why the factor is that 2 over G mu B. That's why to simplify this Heisenberg exchange energy. And anyway, let's consider for the exchange interaction. Between the ith side spin and its neighbor. Then minus 2 summation j, jij, and si dot sj. It is Heisenberg Hamiltonian. The factor 2 is coming from the double counting, because one spin and the other spin cannot be distinguishable, and therefore in the two double counting interaction it is. And anyway, then from this from the definition of the effective molecular field, we can write down this Hamiltonian like that: G mu b si dot bmf, like this. Therefore, this Hamiltonian can be simply write down the effective Hamiltonian is that G mu b summation for I and si dot B is the applied magnetic field in the second term, Gman energy, and Gman energy plus BMF. BMF is the molecular field, effective molecular field generating by the spin Sj. This Hamiltonian, when we consider this Hamiltonian, it is a similar form from the paramagnetic case. Therefore, we can apply this Hamiltonian in a similar manner from the paramagnetic formalism. It is kind of Hamiltonian for a paramagnet. In a magnetic field, B plus BMF. Therefore, we can assume that the molecular field is generated by the magnetic moment in a single spin where there are some spin sublattice. Therefore, let's assume that molecular field is proportional to the magnetization in a sublattice, and basically the lambda is positive for a ferromagnet. Therefore, we can consider that the internal molecular field causes the spin alignment, and this effective Hamiltonian is a similar form from the paramagnetic problem. Therefore, at a critical temperature, and in reality, at a critical temperature means that phase transition temperature of the ferromagnetic order, the thermal fluctuation progressively destroy the magnetization, and also we know the solution of this Hamiltonian, and we already solved from the paramagnetic problem, and the solution was that M over Ms. Ms means that saturation magnetization. It is saturation magnetization M over Ms. The solution is that Brillouin function. Here Bj means that Brillouin function with total spin j, and here and y is defined by that Gj mu b in j over kbt, and in previous case it is a b, but in our case we should consider for the molecular field, and the molecular field is like a lambda m, and therefore the different thing is that the y value is that we consider lambda m but the solution is exactly identical from the paramagnetic solution. And in this case, it is Bj is the Brillouin function. It's a Brillouin function. It is written by 2j plus 1 over 2j cotangent hyperbolic 2j plus 1 over 2j y minus 1 over 2j cotangent hyperbolic y over 2j. It is a Brillouin function. How to solve this problem is from the paramagnetic problem, we already know that magnetization divided by the saturation magnetization, and it is the x-axis is the y. Then there is a saturation magnetization is that it is saturation magnetization value and the 1 or minus 1. And also magnetization shows that Brillouin function. In Brillouin function like that, this saturated behavior like this. It is a Brillouin function. Then we know that anyway, from the T of Tc, at T of Tc is coming from the saturation magnetization, non-zero saturation magnetization, and it starts here. It is T over Tc, and for higher temperature, for low temperature, for example, like this, T is low temperature below Tc, and there are two values. There is here magnetization, finite magnetization value can be defined, and also in high temperature. In high temperature is like 0. It is not seen. In high temperature shows like this, and it is that T is greater than Tc, and also still zero magnetization. But below Tc, only the finite magnetization solution exists. In this case, this is case for the without magnetic field. It is the case for the without magnetic field. B equals 0. And anyway, in this case, from this solution without magnetic field, then we can ignore the applying magnetic field value B. Then we can write down this equation, rewrite, and M is that magnetization is proportional kBt over Gj ubj lambda y from the above equation. And let's consider for the Brillouin function, and for small j, for small y. Small y means that high temperature, at high temperature means that small y, and this Brillouin function can be like that. The approximation for the cotangent hyperbolic y is that 1 over y plus y over 3 minus y cube over 45 plus order of high order term. Therefore, from this approximation, and we can write down as bjy can be summarized in j plus 1 over 3jy plus order of y cube. It is approximation for the Brillouin function for small y. Therefore, from this Brillouin function, and m over ms can be rewrite down m over ms is that j plus 1 over 3j, and so y value. Y value is here, from here, and gj mu b j or kb t and lambda m. Therefore, at the critical temperature, then mm can be cancelled, and also critical temperature, and here Tc from this equation, and the Tc can be write down as Gj mu b, and also J plus 1 lambda ms over 3 kb. Here, ms is that because ms is that ngj mu b, it is a saturation magnetization, and this Tc can be write down as n lambda mu effective moment square and 3 kb. Here, mu effective mass is that Gj mu b over j and j plus 1. Yeah, and here, and therefore the set molecular field is that lambda ms. Then from the lambda ms here, ms can be rewrite down like a Tc, and from this 3 kb Tc lambda ms, and Gj mu b j plus 1. Okay. And I already say that the molecular field is not correct, and when you consider for the spin j equal 1/2, and Tc is about 1000 Kelvin. 1000 Kelvin is very high critical temperature, and which is like iron, cobalt, nickel. In this case, the molecular field can be write down as kbTc over mu b. Then it is about 1500 Tesla, which is very huge value. And to make a spin alignment, the one with Tc 1000 Kelvin, and the molecular field is about 1500 Tesla, and it is unimaginable and very, very huge value. It is unphysical. And anyway, therefore, but the mathematical point of view, and this molecular field theory is very easy to understand. And here, and we, from this point of view, let's calculate the magnetic susceptibility. And magnetic property measurements is that magnetic susceptibility, what DC susceptibility and AC susceptibility. And anyway, the magnetic susceptibility is the basic property in magnetic materials. Yeah, magnetic susceptibility. By applying a small magnetic field, and we already say that magnetization can be write down like this. But the different thing is that the here JJ can be cancelled with each other, and 3 kb. In other words, it is that JJ mu b and J plus 1. But it should be we only by applying it is the result from the without magnetic field. But with applying magnetic field, this lambda m plus magnetic field b plus lambda m by applying magnetic field, and therefore this is that b plus lambda m over t, and therefore we can reduce as TC. TC is that from here, this is a TC. Therefore, lambda ms TC over lambda ms T b plus lambda m. Yeah. From this, TC over lambda ms is that this coefficient in here. Therefore, we can write down m over ms, then 1 minus TC over T, and also in the right hand side TCB over lambda MST. Therefore, the definition of the magnetic susceptibility is that limiting for the small magnetic field, mu 0 m over b is the magnetic susceptibility. Then it is when you consider for this value, and also it is proportional to the 1 over t minus tc. Then which call it is a Curie Bias Law. From the paramagnetic signal, from paramagnetic point of view, and magnetic susceptibility follows that 1 over T dependence. It is a Curie law, and the Curie Bias law is that with applying magnetic field in ferromagnetic materials, there is another contribution for the TC, and therefore the Curie Bias law is that C over T minus TC, rather than TC, but here is theta, and not real TC, but theta, because from other, actually when this material is a perfect ferromagnetism, we can write down theta by the TC. It is a real TC in a complete ferromagnetic materials. But as I said, there are many magnetic systems like antiferromagnetism and ferromagnetism, and can be coexist in certain directions, and therefore the TC value is not exactly same with the TC in experiment. And therefore, the TC is a measure of the magnetic strength, and here the zeta value is a temperature unit, and also we call it is a Weiss temperature. And C is the Curie constant. It is Curie Bias Law. When I make this box, you should memorize. It is ferromagnetic Curie Bias Law. Then how can you understand the magnetic field effect, and also from the magnetization, temperature dependence behavior, and temperature divided by the TC, and also here magnetization divided by the saturation magnetization is 1, and there is an here the spontaneous magnetization. This is spontaneous magnetization. This case, it is that it is 1 at TC. At TC value, it becomes a spontaneous increase of magnetization. But by applying magnetic field and also this smearing effect like this, by applying like this here, by applying magnetic field, and here is the B equals 0. Anyway, it is a limiting case. B equals 0 is a very small field, and for write down for a small field, and it shows that the spontaneous magnetization, and by applying magnetic field, and this smearing out near TC value. How to solve this problem? From the Brillouin function, and we know that the Brillouin function can be written down as j plus 1 y over 3j minus eta y cubed plus high order, and also y value is that gj mu bj b plus lambda m and kbtc. Therefore, the magnetization m over ms is that Brillouin function is that j plus 1 over 3j gj mu bj b plus lambda m, it is y, kbtc minus high order y cubed from this y value, anyway, here from the above, and molecular field defined like this. Therefore, gj mu b over kbtc is that 3 over lambda ms J plus 1. Here, therefore, by continuing for the M over Ms, is that J plus 1 over 3J and 3J lambda Ms J plus 1 P plus lambda M minus eta y cube. Therefore, cancel with each other, and in this case, B plus lambda M and lambda Ms minus order of y equal 3J B plus lambda M over J plus 1 lambda Ms cube. And here the y is that 3J over J plus 1 and B plus lambda M over lambda Ms. And for spin J equal 1/2, and it is 3/2 and 3/2 cancel with each other, and the y is that B plus lambda M over lambda Ms. And therefore, the Brillouin function is proportional to the B plus lambda M to the cube, and that's why we do not ignore this lambda y cube term, because the cube term is important. And anyway, then from these two equations, and there it is the two different equation, and the first and second equation can graphically solve the problem. And anyway, and here the saturation magnetization behavior and the Brillouin function shows that like this. This is a Brillouin function solution. And also from the second equation, at here at certain value, anyway, it is M over Ms, and this is y. And T equal TC value is that higher than temperature Tc. I'm sorry. Tc greater lower than the temperature lower than Tc, and it shows that this value, and also and we can interpret like that, and the T of Tc and so with increasing the temperature, T is greater than Tc like this. And anyway, this point is that Gj mu b Jb over kBt. This is the case for the under magnetic field. Without from the previous one is the without applying magnetic field, Yeah, here without applying magnetic field, it shows that like this, but in our case, and it is shifted to the y direction as an amount of this value, and that is the from the magnetic field effect, and this is magnetic field effect. Here, and we found that in summary, we can say that from the Curie Bias law is important, and by applying magnetic field and without magnetic field, it shows that the spontaneous magnetization, and by applying magnetic field, there is a finite magnetization value, and also it can be graphically solved. And the Curie Bias law is the result of the ferromagnetic interaction, and the zeta value is the interaction, molecular field interaction.